Before you view this video, you should have already seen the Fingerprint Paradigm Pore video clips 1, 2, and 3. If it's been a while since you saw it, take a few minutes and watch it again. I purposely produced that video in a no commentary format. With this follow-up video, I'm going to provide my interpretations of what I filmed. To help explain the Pore 1, 2, 3 video clips, I first have to mention the seconds timer at the bottom of the screen. This stopwatch displays seconds in real time, so you can see how quickly or slowly the friction ridges respond. Each skin response can be accurately associated with the second that it occurs. In the introductory video, you also examined captured frame grabs that displayed the friction ridge response along with the second that recorded the time. The timer is useful in observing both the video and later the captured frame grabs or photographs. Since there is no ink or powder on the finger, the initial challenge in this tutorial is for you to interpret the two elevations of friction ridge skin, the raised ridges and the recessed furrows. I'm going to designate my interpretation of ridges with a black arrow. Now I'm going to designate the furrows with a white arrow. These colors correspond to black ridges on a fingerprint card and space between the ridges, the white voids from the furrows. Again, since there is no ink on the skin, I'm just using the color differentiation to distinguish the ridges and furrows. Sir Francis Galton conducted extensive research and authored many publications and books about fingerprint identification. His books Fingerprints established many of the identification methods and principles still in use today. In the publication Decipherment of Blurred Fingerprints, Galton explained how to compare fingerprints, and he introduced and illustrated a process he recommended for comparing fingerprints together. Galton gained access to fingerprints from the same person taken years apart, in 1878 and 1892. These were acquired because he sought to determine if fingerprints changed over time. He called these fingerprint exemplars doublets, and they were ground truth exemplars of prints taken 14 years apart. Galton's plan to prove fingerprint permanence or persistence, that prints do not change over time, involved a skillful knowledge of photography and the enlargement of the doublet prints to 7 times their actual size. He then utilized tracing paper and with a pencil carefully sketched over the ridges, defining them with a narrow line. He then drew small circles at the ridges that terminated between the furrows. In addition to this extensive documentation process, he drafted a narrative that explained each ridge feature he noted to exist in compliant positions in each print. This is one of the fingerprints from 1878 that Galton documented with his skeleton line chart system. I'm going to change the color of the print and begin the process of drawing skeleton lines on the ridges using a paintbrush program. I'm simply using the pencil tool and with the mouse superimposing the skeleton line in the center of the ridge, trying to stay in the center just as Galton did with tracing paper. Next, I'm going to draw circles at the ridges that terminate within the furrow. These terminating ridges are called ending ridges or ridge endings. Now I'm going to bring in Galton's skeleton line of the same finger. Here you can see clearly the ending ridges I marked and the ones marked by Galton. These charts help support that Galton and I recognized the ridge structure in a similar manner. With Galton's skeleton chart, I know exactly what he interpreted. I scanned the 1878 fingerprint into an automated fingerprint identification system so the computer's algorithm could also process the friction ridge images. The computer generates a graphical image of the ridge structure it interprets and digitizes. The image it generates is called a skeletonized image. Now I'm going to display Galton's skeleton chart, my skeleton chart, and the skeletonized image from the automated fingerprint system. I can advance the comparison process by bringing in the chart the APHIS made, and here you can see the ending ridges that APHIS designated. Additionally, the APHIS designated bifurcating ridges, ridges beginning as one ridge and forking to become two ridges. A lot more of that later in the fingerprint paradigm. I'm now going to interpret and skeletonize this print from the video clip and designate the ridges with black lines. I'm also going to designate the furrow area with white dotted lines. The ridge structure is now marked, and I can proceed to reviewing video clip number 1. Let's revisit video clip 1 and first interpret the raised ridges designated with the black skeleton lines. Now let's advance the video and keep an eye on the seconds timer and watch the friction ridge response to the breathing stimulus. You should now make the ridge structure interpretation and observation from the pores responding with fluids filling their orifices. The fluid in the pore response is visible because the camera has 8 LED lights on during the filming process. The LED light is an important visual aid to our interpretations and observations because the reflectance is very noticeable and sensitive to the presence of fluids in the pore. Here are 3 selected frame grabs to evaluate from the Pore 1 video clip. Clearly at 12 seconds, there is a significant pore response visible. The camera's light reflectance of emerging pore fluid is very obvious. Even though the photographs are only 2-dimensional, the light can be seen reflecting on the fluid in the recessed elevations of the pore duct that gradually becomes visible. The complete friction ridge response began, progressed, and stopped, and then returned to the original skin condition in a span of only 30 seconds. I describe this 30-second activity as a dry to wet to dry friction ridge response. Most significant to this observation is the friction ridge skin photographs at 0 and 30 seconds appear to be completely dry, while the 12-second photograph displays significant fluid in the pores. In my assessment, during this controlled breathing cycle, the pore functions in a manner that introduces, exposes, and retracts the fluid, all in a period of only 30 seconds. Here is another example of pore response in Pore video clip 2. But let's review the video with a focus on a single responding pore from start to finish. Notice all the clearly defined pores visible from the camera LED lights. But then move your eyes to the magnified pore. In this magnified clip, the dry to wet pore reaction is clearly observable, and the pore completely disappears after the fluid returns to the pore duct. This active pore is virtually invisible in the video until it responds to the breathing stimulus. Notice that at a certain point in time, all 8 LED lights can be seen reflecting in the active pore. Now let's look at the advantage of assessing timestamp photographs. The array of photographs clearly display the invisible pore, a slight reflectance that proceeds to multiple lights that enlarge to 8 separate lights at 10 seconds. At 16 seconds, the lights disappear, but fluid is still visible. A small light reflectance is visible, and eventually the pore disappears, and the 28-second photograph looks almost identical to the 0-second first frame. At 0 and 28 seconds, the friction ridge appears to be completely dry, and the pore in the cropped area is not responding. Now let's review photographs of the pore response in video clips 1 and 2. Both of them display the dry to wet to dry response. Consider this response when we review pore video clip number 3. Video clip 3 is significantly different than the other clips. Video clip 3 begins with visible pores responding to a breathing stimulus, and the friction ridge surface appears to be wet in both the pore structures and in the furrow area. Despite the considerable amount of fluids present on the skin, the fluid appears to completely return back into the pore ducts, and even in the furrow area, the skin appears to be very dry. The wet to visibly dry surface area of the friction ridge skin in this short period of time illustrates again how effectively and quickly pores can produce and retract fluids on friction ridge skin. In this display, I used red circles to designate the responding pores to display their population on the skin. In my interpretation of the response, I can classify these pores as active pores. Active pores are orifices that respond to stimulus by releasing fluids onto the friction ridge skin. I described them as active because I could clearly see and document the fluid in the orifice because of the reflectance of the camera's LED lights. Active pores is one classification of pores based on the pores releasing and retracting fluid from the pore duct. The opposite of active pores would be inactive pores. Inactive pores are orifices that do not respond to stimulus, and there is no release of fluids onto the friction ridge skin. I use the active pores to help me visualize a perimeter for the inactive pores. In this chart, I have designated 3 inactive pore fields and used a yellow dotted perimeter to define them. Let's do a quick review of the Pore 1, 2, 3 video clip interpretation and observations. First, we see the seconds timer and recognize that it can be used to timestamp skin reactions of the in situ friction ridge skin. Purposely, there is no ink or powder on the fingers, so you must interpret ridge structure by skin coloration only. Now we are looking at an array of 10 sequenced photographs extracted from the video that display the pore response at different intervals. Maximum pore response was at 14 to 16 seconds. Here we see captured video and frame grabs with the timestamp, both methods to document skin response. In this frame, we recognize our concentration is on the 2 elevations of friction ridge skin, raised ridges and recessed furrows. This view shows the raised ridges in black arrows with the furrows displayed in white arrows. Let's never forget the significant contributions Galton made to the discipline of fingerprint identification. All of his publications are available at galton.org. Galton acquired these prints taken 14 years apart as part of his research on friction ridge persistency over time. A comparison of my skeleton chart on the left and Galton's chart on the right. With this documentation process, one can see the interpretation of compliant ridge structures of two examiners. Here we have two manual skeleton charts and the APHIS chart on the right, made by the automated fingerprint identification system. This is a photograph depicting the LED lights reflecting in the pore orifices. What I consider to be a textbook example of the dry, wet, dry friction ridge response to a breathing stimulus. The right photograph clearly depicts a 12-second friction ridge response. In this inquiry, we observed a highly magnified single pore. This clip indicates that at 17 seconds, the pore reflects all of the LED lights from the camera. These 14 photographs display a complete dry to wet to dry cycle of a single active pore. Pore video clips 1 and 2 were similar. Pore video clip 3 was a wet to dry friction ridge response. The 30-second frame grab displays friction ridge to be very dry compared to the starting point. All fluids seem to have vacated the ridges and furrows. Here I designated active pores with red circle callouts. And finally, I noted 3 inactive pore fields and marked them with a yellow perimeter. In summary, you've examined ground truth exemplars of friction ridge structure responding to controlled breathing exercises. This breathing enables you to see how pores respond in the furrows and on the ridges of the friction ridge skin. The breathing exercises were Pore video clip 1, holding breath, then breathing very hard. Pore video clip 2 was a fast and non-fatal neck chokehold to a student volunteer. Pore 3 was fake induced laughter. Stay tuned for more tutorials at fingerprintparadigm.com.